I'd like to talk about the use of washer-shaped objects to calculate the volumes of certain solids of revolution. I will assume that you're familiar with the basics of solids of revolution, including how to use cylindrical or disc-shaped objects to calculate the volumes of certain solids of revolution. If any of that is unfamiliar to you, I would invite you to watch my introductory video on solids of revolution. Okay, now I'd like to pose the following question. How would I approximate the volume of the solid of revolution I would get if I rotated the blue circle that I just drew about the black line that I just drew? Okay, so think about that. The solid of revolution would be some kind of donut-shaped object. So let me draw what that would approximately look like. All right, something like that. Now, so how would we approximate the volume of that donut-shaped object? Can you see that using a set of cylinders wouldn't work out so well? Okay. The problem with using a set of cylinders like the ones denoted by the purple figures that I just drew is that they don't properly account for the hole in the donut. All right? So what we would want to use instead of cylinders or discs is we want to use washers. All right? And I'm defining washers as cylinders with a hole cut out of the middle. All right? So the top view of a washer would look like what I've just drawn there. Okay, it would be it's a cylinder with a hole cut out. So from the top, you would see a circle, and then there would be a circular hole in the middle. All right, so a set of washers is one way to approximate this volume. Now, let me discuss what the volume of a washer is. Let's say that I wanted to calculate the volume of a washer with a height h and an inner radius of R1 and an outer radius of R2. So let me label R1 and R2 in my top view of my washer. Okay, so one way to calculate the volume of that washer is first to calculate the volume of the corresponding solid cylinder. That would be pi R2 squared h, if the height is h, and then simply subtract the volume of the hole. And the volume of the hole is pi R1 squared h. Okay? And so that is the formula that we will use when we use washers to set up integrals to calculate the volumes of certain solids of revolution. Now, you can factor out the pi and the h from our formula, and so you can write it more compactly as pi h times the difference of R2 squared and R1 squared. Okay? So that's the basic idea regarding using washers to calculate volumes of solids of revolution. Now, let's do an example using washers. So give me a minute to make a picture. Okay, I've drawn a portion of the graph of x squared, and I've also drawn a portion of the graph of x. As you can see, there's a region defined by the set of points less than, or the set of points below the graph of x and above the graph of x squared. Now, let's define a solid of revolution by rotating that region about the x-axis. Okay, so there's a rough sketch of what that solid of revolution would approximately look like. And now let's set up the integral. So we will imagine sets of washers approximating the volume of our solid of revolution. All right, and so the inner radius of our washers is going to correspond to x squared, and the outer radius is going to correspond to x. So the integral is going to be the integral from 0 to 1. That's because the region corresponds to x values from 0 to 1. The two graphs intersect at the origin and at the point 1, 1. All right, and so the integral we want is pi times x squared minus x squared squared with respect to x. Okay? Think about the washer formula that I was discussing a few minutes ago, and see how that integral is using the volume formula for a washer. All right, so let's go ahead and solve this integral. So we'll get pi x cubed over 3 and pi x to the 5 over 5. And we'll evaluate that with respect to the limits of integration. When I plug in 0, I'll get 0, so I only have to evaluate it with respect to 1. So that'll give pi over 3 minus pi over 5. And let's see, what is that equal to? That's equal to 5/15 minus 3/15 pi, or 2 pi over 15. Okay? Now, let's do a related example. What if instead of rotating that same region about the x-axis, I rotated it about the y-axis? So let me make another copy. Let me make a picture, a copy of the original picture with the original region. So give me a minute. Okay, and so now we're going to rotate it about the y-axis. So let me draw what that would approximately look like. All right, something like that. And so we will stack washers to approximate the volume. So now the inner radius and the outer radius are going to correspond to x values. So let's invert our original functions. So originally we had y equal to x squared. That's going to correspond to x equal to the square root of y. And then we had also y equal to x, and that's its own inverse, x equals y. And so the integral that we're going to set up is going to be the integral. So the y values go from 0 to 1 just like the x values went from 0 to 1. That's not always going to be the case, but for this one it is. So the integral from 0 to 1 of pi times the square root of y squared minus y squared with respect to y. All right, so take a minute to make sure you understand why that is the integral that we have to use. Notice that the parabola corresponds to the outer radius, the bigger radius, and the straight line, the y equals x, or x equal to y, that corresponds to the inner radius, if you could imagine a washer. Okay, so finishing off this integral. So the square root of y squared is just y, so that'll give me pi y squared over 2, and then minus pi y cubed over 3. And we'll evaluate that at the limits of integration. So I get pi over 2 minus pi over 3. A half minus a third is equal to 3/6 minus 2/6. That's 1/6. So pi over 6. All right. Now I would like you to try to do an example. Okay, so here is the exercise I'd like you to do. I'm going to give you two functions. And the plots of those two functions are going to define a region, the set of points above one of the functions and below the other function. I'd like you to find the volume of the solid of revolution defined by rotating that region about the x-axis. Okay? So pause the video and try to do that now if you like, please. All right, so I'll go ahead and work it out as well. So, as always, I'll make a picture. So the graph of x minus 1 quantity squared, that's a parabola with its lowest point at 1, 0. And the y-intercept is 1, so it'll look something like this. And then the graph of the square root of x minus 1. So the domain only includes points greater than or equal to 1. And when x is 2, y is 1. So it'll look something like that. So the solid of revolution is going to look something like this. And the integral that I'm going to need to solve is the integral from 1 to 2 of, because the points of intersection are 1, 0 and 2, 1, if that wasn't clear. All right, so the integral from 1 to 2 of pi times the square root of x minus 1 squared minus x minus 1 squared, that whole thing squared, so I'll just raise it to the 4th power. And the integral is with respect to x. Okay, so now let's work that out. So let me first simplify. So pi times x minus 1 minus x minus 1 to the 4 dx, and let's use a u substitution. I'll let u equal to x minus 1. So the derivative of u with respect to x is equal to 1. So the integral that I need to do now is the integral from 0 to 1 of pi times u minus u to the 4, all with respect to u. So that gives me, let's see, pi times u squared over 2 minus pi times u to the 5 over 5. And I have to evaluate that at my limits of integration. When I evaluate it with respect to 0, I'll get 0. So I end up with pi over 2 minus pi over 5. And that's equal to, let's see, 5 over 10 minus 2 over 10 gives 3 over 10, so 3 pi over 10. All right? Now, I'd like you to do the following example. The more examples, the more sure we are that you understand. So this time, the functions for the problem are the following. And once again, the plots of these two functions are going to define a region with respect to the set of points above one of the plots and below the other plot. And I'd like you to rotate that region about the x-axis again and find the volume of the corresponding solid of revolution. All right, so pause the video and try to do that now if you like. All right, so I'll go ahead and work it out as well. Let me make a quick picture. So x squared plus 2, that's a parabola shifted up by 2. X plus 4, that's a line with a slope of 1 and a y-intercept of 4. So let's see, where do the graphs intersect? So they're going to intersect where x squared plus 2 is equal to x plus 4. And you may need to do some algebra to determine the points of intersection. That's normal. So we have to solve x squared minus x minus 2 equal to 0. That gives x minus 2 and x plus 1. The product of x minus 2 and x plus 1 equals 0. So x equals 2 or x equals minus 1. So now we know that the points of intersection are minus 1 comma 3 and 2 comma 6. Okay, and so that completes my drawing of the region. And so now the solid of revolution is going to look something like the following. All right, so let's set up this integral now. So the line is going to correspond to the outer radius of the washers, and the parabola is going to correspond to the inner radius. So the integral from minus 1 to 2 of pi times x plus 4 squared minus x squared plus 2 squared, and the integral is with respect to x. So let's expand those terms, and I'll remove the pi, or pull it out of the integral. So x squared plus 8x plus 16 minus, and be careful with because you're subtracting the second term, minus x to the 4 minus 4x squared minus 4. Okay, and let me clean it up a little bit first. Okay, so let's see, can we simplify? Yes, we can. So combine the squared terms, minus 3x squared. 16 minus 4 is 12. So we get pi times the integral from minus 1 to 2 of minus x to the 4 minus 3x squared plus 8x plus 12. And so that gives pi times minus x to the 5 over 5 minus 3x cubed over 3 plus 8x squared over 2 plus 12x, and we'll evaluate that expression at the limits of integration. All right. So let me check that. Minus x5 over 5, then 8x squared over 2, 12x, minus 3x cubed over 3. So you plug in, you evaluate that expression at x equal to 2 and at x equal to minus 1. Now I don't have room to work out the what all the terms are, but I'll tell you that once you evaluate the terms at the limits of integration and simplify, well, the answer will be 162 pi divided by 5. Okay? I'd like to end with a volume calculation involving the rotation of a region about a vertical axis. All right? So it's important to make sure you can do those types of problems. So the following equations will define a few plots, and those plots will define a region. So the square root function, the vertical line x equal to 1, and the horizontal line y equal to 0, in other words, the x-axis. So when you plot those, you will see that they define a region. And I'd like you to do the following. Calculate the volume of the solid of revolution defined by rotating the region defined by the given equations about the x equal to 2 line. All right? So pause the video and try to work that out now, please. Okay, so I'll go ahead and work it out as well. So we want to calculate the volume of the solid of revolution defined by rotating the region defined by the given equations about the x equal to 2 line. So I will sketch the solid of revolution. So give me a minute. All right, almost done. So there is a approximation to the solid of revolution we're focusing on. We are rotating the region that I'm shading in yellow right now about the blue vertical line, and so that'll give us the necessary solid of revolution. Okay, so continuing. So now we need to determine the expressions with respect to the inner and outer radius. Can you see that the inner radius is always going to be 1? That's because the distance between 1 and 2 is 1. Okay, and so if we stack a bunch of washers, they're all going to have the same sized hole. And then the outer radius is going to correspond to 1 minus an x value. So let's invert the square root function. So we have y equals the square root of x. That corresponds to x equals y squared. So 2 minus y squared is the outer radius. Putting it all together now. So we're going to integrate from 0 to 1 because the smallest y value is 0 and the biggest y value is 1. And we're going to do integrate pi times two minus y squared squared, that's the outer radius expression, minus 1 squared, that's the inner radius expression. And the integral is with respect to y. Okay. Now we can finish this off. So the integral from 0 to 1 of, let me move pi outside, so 4 minus 4y squared plus y to the 4 minus 1. So I can simplify. 4 minus 1 is 3. So what do I have left? I have the integral of, or pi times the integral from 0 to 1 of y to the 4 minus 4y squared plus 3 with respect to y. And so that'll give me pi times what I get when I evaluate y to the 5 over 5 minus 4y cubed over 3 plus 3y with respect to 1 and 0. When I evaluate with respect to 0, I'll just get 0. When I evaluate with respect to 1, I'll get 1/5 minus 4/3 plus 3. 1/5 minus 4/3 plus 3. I won't work that out, but I'll tell you that that'll give me 28 over 15. So the final answer is 28 pi over 15. Okay, and I hope that's what you got.